Okay, all right. So, hello and welcome to the Daily Space for Tuesday, May 15 of 2018. I am Dr. Andres Plazas, and today I am sitting for Dr. Pamela Gay, who, in her own words, has failed to time zone, and she needed to be two places at the same time. So, Pamela has a lot of superpowers, but that's not one of those yet. So, as always, we are going to bring you a roundup of today's news from space and astronomy. And today we're going to have three stories, one about black holes, another one about exoplanets, and the last one about the multiverse. So let's just go and see what we have today. So in today's top story, the journalists claim that our sun has 2 days left, as you can see by these headlines, a little bit crazy. But well, luckily journalists are often bad at communicating science. And actually, what do they mean? What's the research about? So the actual research at the first story that we have today is that astronomers from Australia have found that the fastest growing black hole in our universe. So what did they find? They found a black hole about from about 12 billion years ago in the age of the universe. Let's remember that the age of the universe is about 14 billion years. So this is an object that is from the early stages of our universe, and it has about 20 million solar masses. And why do they say that this is the fastest growing black hole known in the universe? They said, in technical terms, that it shows a 1% growth rate every million years. So that's a little bit technical. What does that mean in normal terms? It says that it eats one solar mass every 2 days from the accretion disk. So this is a black hole that is most likely in the center of a galaxy, and it has an accretion disk around it, and all that material is falling into the disk, and then hence it becomes very bright. And this is an object that is called quasar or quasi-stellar object because it actually looks like a star. They are very, very far away. They look like a star, but they are very bright, so that's why we can see it. So these researchers, they have used a telescope from Australia called the Sky Mapper telescope, and they have looked at light in the infrared. So let's remember the why in the infrared. Let's remember that this object is very far away in the universe. So due to the expansion of the universe, when that light makes it to the Earth, uh, the wavelength in which we can detect this is the infrared light. And then what they have used what we call a spectrograph, which is basically an instrument that allows us to split the light like a prism, and then we can analyze the spectral lines from the light coming from this object. Well, in addition, I also think that it's interesting that they have used data positions from a data set called Gaia. About 2 weeks ago, the Gaia collaboration actually launched the position of about more than 1 million objects in the sky. And they have also used this data set in order to find out that this object is very, very far away. They do it through the technique of parallax, as you may have heard in this show before. So the large amount of gases that fall into the black hole, they produce a lot of large quantities of heat due to friction. So this is why this object is very, very bright. And according to one of the researchers of this study, Dr. Christian Wolff, he says that if this galaxy were sitting at the center of our own Milky Way, it would appear about 10 times brighter than a full moon. It would appear as an incredibly bright point star that would almost wash out all of the stars in the sky. So this is interesting because the researchers also say that if this object existed in our own galaxy, the large amounts of X-rays would not have allowed the development of life in our Earth. Remember that X-rays are very energetic forms of the electromagnetic spectrum, and if you have your planet that is being bombarded by a lot of high energy rays, then you probably it's gonna be hard for you to form life as we know it. These objects are also very rare, so scientists they still have to understand how this particular object grew so large in the early stages of the universe. So let's remember the universe started about 14 billion years ago, and this is an object about 2 billion years ago. So in cosmic terms, it's a little bit at the beginning of the universe. So there hasn't been too much time to understand why it is so large and why it has become so bright. But we still have that puzzle, but at the same time, this is an object that can be used as a beacon of the early universe. In the early universe, we didn't have still galaxies, we didn't have still stars. So there was an epoch called the Dark Ages of the early universe, where you didn't have any formation of galaxies of stars. But since this is an object from those early times of the universe, as I mentioned, these objects can be used as beacons to see and study the formation of elements in the early stages in the early galaxies of the universe. So yeah, just to wrap up, so we wanna, as I said, these are very rare objects. Now we would like to find more of these type of objects within the next generation of the instruments, and then researchers and astronomers they expect to use these type of quasars to measure the expansion of the universe at that early rate. So yes, this is our first story of the day, and now I would like to talk to you about a little bit exoplanets. So as usual, if you have any questions of any of the stories we're talking about, we can leave them for the end, and I'll be happy to answer, stay for a few more minutes and answer any questions that you may have. But now we're gonna talk about another story that we think is pretty cool, and this has to do with exoplanets. So as you know, in astronomy, one of the fundamental questions that we would like to answer is, are we alone in the universe? So we are actually doing a lot of research in order to find other planets that could harbor life as we know it. This is our starting point. Of course, there could be life that doesn't resemble at all what we know here of Earth, but we have to start somewhere. So we say, okay, we know a planet where there is life, and that is Earth, and that's why we look for planets that are similar to the Earth. And what do we mean by that? The planets that actually are rocky in nature, that are around the stars that are similar to our Sun, and that are in a location that is not too close or not too far from the star. So this is what is called the habitable zone, or the Goldilocks zone, because of the tale for children. Not too close, not too far. And why do we want to be not too close and not too far? If we're too close to the sun, then the water is going to evaporate. If we are too far from a sun, then the water is going to freeze. And we need water in its current state, and as we know, to develop life, carbon life, as we know it. However, the research that we are going to talk about today shows us that these conditions might not be enough to ensure that we're going to find possible life in a planet. So the researchers in this story, they say that other parameters might need to be taken into account. In particular, they talk about the tilt of the relative to the orbital axis, is what is called the obliquity. What is this tilt? In our Earth, there is the tilt of the rotation axis of the Earth is of about 23 degrees, and this is because this is the cause of the seasons, of the 4 seasons that we find in the torrid zones of the Earth. So on the Earth, if you are at a latitude higher than 23 degrees or lower than minus 23 degrees, then you're gonna find the 4 seasons, as you know. And this is because this number coincides with the orbital tilt of the Earth. So as I was saying, there is this factor, the orbital tilt of the orbital axis, and also the eccentricity of the orbit of the planet. So the eccentricity is a number that tells you how circular the orbit of a planet around a sun, around a particular star is. So we know, because of astronomy, because of the laws of physics, what we call the Kepler laws, that the orbits of the planets in general are ellipses. They are elliptical. However, the orbit of the Earth is not that elliptical. Actually, the eccentricity is very, very small, and the orbit is close to circular. And the question that these researchers want to ask is, or they want to tackle is, what happens if I change the eccentricity of the orbit of the Earth? What's going to happen with the potential of harbor life? And at the same time, what happens if I change the tilt of the Earth with respect to the rotation axis? So it would be great if we had powers and we could actually do an experiment and take a giant robot and move a planet and change the ellipticity and the tilt, but we cannot do that, unfortunately, yet. What we can do is we can use simulations, we can use computer. So this is exactly what they did in this study. The authors use computers, they use computer modeling, and then you can plug in the laws of physics, and then you can just basically change the tilt and the eccentricity of the planet as much as you want. And then you can see how these factors impact the potential for life. So our own Earth, it wiggles a little bit over millennia, over many years, and the authors, they want to answer what would happen if those wiggles were larger. They actually found out that the planet could enter into what they call a snowball state. So that would mean that it would completely freeze if the eccentricity is too large or the tilt is larger than 35 degrees. So this came a little bit as a surprise, because previous research had shown that if you increase the tilt of a planet, then you would actually make it warmer, of an Earth-like planet, it would actually make it warmer. But what this study found is that it would trigger what we have called here on Earth ice ages. So this study has shown us that ice ages on exoplanets can be much more severe than on the Earth. And it also has shown us that the orbital dynamics of a planet, the orbital dynamics being the eccentricity and the tilt, these two parameters can be a major factor when you want to decide about how habitable a planet is. So it's not enough that you find a rocky planet like the Earth and you find it going around a star like our Sun in the habitable zone. You need to take into account more factors such as this one. So another important thing to say or to note about this study is that all the simulations and modeling, they help us decide which Earth-like targets we want to follow up with ground-based telescopes. So as a general rule of thumb, the time in a telescope on Earth is very precious, right? You need to know in advance, and you need to justify where do you want to spend your time observing at the sky. So if you have a probe like Kepler or like TESS that is looking for exoplanets, Kepler has found thousands of exoplanets, and TESS will find many more exoplanets. So it is not possible to actually follow up each one of all of these to see if they are like the Earth. But if you, for example, have two possible Earth-like exoplanets candidates, you can resort to this type of modeling to see like, oh, but this other planet has a lot of tilt and a lot of eccentricity, so maybe the potential for life is not going to be that large. So let's point at the other exoplanet. It is more likely for us to find life in the other one. So yeah, so that was pretty cool as well. I also like exoplanets. I am a cosmologist myself, but I enjoy learning and reading a lot about exoplanet research. But for our last story of the day, we're gonna talk a little bit more about cosmology, which is the study of the universe as a whole, by definition. So the last story that I'm showing here, sorry, I forgot to change here now you can see my slides. Well, sorry for that. Well, as I was saying, the last story that I want to talk about, that's better. It's a story about the multiverse. So there is this question that is that this paper wants to talk about, and is, could a multiverse be hospitable for life? What does that mean? So what is the multiverse? The multiverse is an important question in cosmology. So we have our universe, and I want to clarify that so far we have no experimental evidence of a multiverse, but that doesn't stop a lot of theorists and physicists and astronomers to come up with the idea that our universe is just a part of an ensemble of many other universes that we call the universe. And it could be that in another universe the laws of physics are different, the fundamental constants of nature, such as the speed of light, of the charge of the electron, all these numbers are different. And they have come up with this idea to to try to understand some of the properties that we observe in our universe. One of those properties is what we call the accelerated expansion of the universe, which is caused by something called dark energy. So, just to recapitulate a little bit, about 100 years ago, it was found by Edwin Hubble that the universe is actually expanding. And then people actually thought, well, if the universe is expanding and it's not empty and it has galaxies and it has planets and it has gravity, that gravity should be slowing down the expansion, that expansion of the universe. In the same way that when you throw a stone to the sky, you would expect it to be slowed down by the gravity of the Earth and then come back to you. However, in 1998, they found out actually the exact opposite, that the universe, instead of being slowed down, the expansion of the universe of being slowed down, is growing faster and faster with time. So that is to say that you have a velocity that is increasing with time, and that is the definition of what we call an acceleration. So we have observed what we call the accelerated expansion of the universe, and we have no idea of what it is. So we have two options. Either we have to modify the laws of gravity that we have currently to describe um, our universe. These are laws of gravity that are very successful. Or we introduce a new component of the universe that has some sort of negative pressure that is causing the universe to expand at a faster rate every time. And this is what we call dark energy. So dark energy is related to the formation of a structure and of galaxies, because what is dark energy doing? So you can imagine that you have dark energy on one side and you have all the structure of the universe, dark matter, which is different despite being called dark as well. You have dark matter on the other side and galaxies that all have gravity. So you can think of this as a cosmic tug of war. If you have a lot of dark energy, then the dark energy is going to win this tug of war, and then you're not going to form a lot of large structure in the universe. And then you're not going to have galaxies, and then you're not going to have solar systems, and then you're not going to have a planet like the Earth where you can find life. If you have just a little bit of dark energy, then you have a slower expansion of the universe, and it could be that the gravity of the structure of the universe actually wins in the end to dark energy, and then we could actually recollapse in billions of years in what we call a big crunch, as an opposite to a big bang. So it turns out that the amount of energy is related to how a planet, how a universe, a particular universe, could harbor life. As I said, if you have a lot of dark energy, you don't have time to form a structure in the universe, and hence you don't have planets. So the amount of dark energy that has been measured in our universe is very small to what you would expect from theory. So we have a very sound and solid theory that is called quantum field theory. That is the theory of the microscopic, so to speak. And if you think that the vacuum itself has energy, that could be a candidate for what it could be dark energy. We know from experiments, that's a fact, that the vacuum has energy. This is a consequence of quantum field theory of quantum mechanics. However, when you do the calculations and you add up of this energy of the vacuum, it gives you, and if you say that that could be the dark energy, it gives you a value that is way larger than what we observe. So a lot of cosmologists, like tying back to our story, a lot of cosmologists have thought, well, maybe this is a puzzle, but maybe we are actually living in a multiverse, and there are a lot of other universes where actually dark energy is very large, and you don't have any formation of a structure at all. So you cannot form any life. And because you have these large amounts of universes where this happens, we just happen to live in the universe where the amount of dark energy is just right that life was able to develop. So this is an argument that a lot of cosmologists and astronomers don't like, because it kind of makes us sound special, and we don't like that. We don't in astronomy. Astronomy has taught us that first we thought that we were the center of the solar system, then we thought that we were the center of the galaxy, then we thought that we were the center of the universe, and cosmology has taught us that actually we don't live in a particularly special place in time or space in the universe. This is what is called the Copernican principle, as a consequence of what is called the cosmological principle. So the idea that we live in a universe that has the right amount of dark energy is, we don't like it that much, but, well, it could be. So what did these people do? These people again use simulations, because again we only know this universe, so we don't have the power to create a lot of multiverses in the lab. That would be cool, but we don't yet. So, well, I don't know. So these researchers use simulations in which they tune the amount of dark energy, and then they assess the impact on the formation on planets and galaxies, on stars. So they found out that actually the questions that they were asking is, how much dark energy can be there before life is impossible, and how do you measure that? If you don't end up forming any stars, then there's no life that's going to be possible, right? So they found out that even if the universe has 100 times more dark energy than observed, then stars would still form and life would still be possible. So the question still remains, given these results, why don't we see a larger amount of dark energy in our universe? So they go to the people who posit this hypothesis of the multiverse, and they are telling us that we observe a small amount of dark energy because that's the only way it could have been. Otherwise, there would not be life and we would not be here. But then the simulations are telling them, like, well, actually, if you have a larger amount of dark energy, you would still have a decent amount of star formation. So it would be possible still to have a planet that could harbor life. So this is another step in that direction, like another example of using simulations of what could and could not be answered. And well, the question remains, what is dark energy, and why is the amount of dark energy that we measure so small, and why life has evolved in the universe, what has made us so special. So okay, yeah, well, that's what I wanted to tell you guys today. So I'm gonna stay a little bit and look at the chat. I haven't actually looked at it, but I'm gonna take a look. And let me know, guys, if you have letter questions. Yes, my last name has more letter nows. Mm. Dark energy and dark matter, yes, they're very, we don't know what they are. They constitute about 95% of the universe, and they share the adjective dark, and sometimes that makes it confusing when you see it in the news, but they're very different. And we're still looking with a lot of research in cosmology right now is going through to find out what dark energy is, what dark matter is. We're trying to find direct evidence for dark matter. We think it could be an elementary particle that we still haven't detected, that is very hard to detect. We're also looking at astrophysical signals and see that it could be the consequence of dark matter. But just to make a little the distinction a little bit more clear, the scales on which dark matter operates, so to speak, is on galactic scales. It's binding galaxies together, even binding clusters of galaxies together. And these are scales that are very large compared to us humans. But the effect of dark energy is on scales that are much, much larger than galaxies and clusters of galaxies. These are like 100 millions of light years of scales that we're talking about. And the effect of dark energy, despite dark energy being so small as I said, the effect of dark energy in the end is causing the universe to expand at an accelerated rate. And again, this is the idea that fits the current data. It could be that we have to modify the laws of gravity, and that's why it is so important to find out more about what this component might be. Okay. It says, can you talk about emergent entropic gravity theory versus dark energy? I'm actually not an expert on emergent gravity. I don't know if you're thinking about Eric Svelinder's gravity. So it's an alternative to dark energy. So yes, I'm unfortunately, and I apologize, I'm not an expert on that theory. I do know it is an alternative to the existence of dark energy. Many scientists they wanna posit that actually there is no dark energy. Could be that gravity behaves in a different way at different scales. One example of this is what is called the modified Newtonian dynamics, that is trying to explain dark matter. So let's get not confused a little bit here again. I'm talking about dark matter and dark energy. The question was about Eric Velinder's theory of gravity versus dark energy. And I do know that is an alternative explanation of gravity, but I don't know a lot of the details to talk more about it. But I was just positing the example that this is an important area of research. And for example, to explain away dark matter, some people say maybe um, gravity needs to be modified in the scales of galaxies. And actually, this theory somehow agrees with observations on the scales of galaxies. But the point is that if you're going to apply that same theory to the large scale structure of the universe, to the cosmic microwave background, that theory actually doesn't match what the hypothesis of dark matter gives you. To come back to, and one last more thing to say about dark energy versus Eric Velinder's gravity is like now we would have to compare with observations. In the end, that's how you decide. I'm not sure exactly how many predictions has the theory of Velinder made, or what observables could be gathered in order to actually tell the difference between the current hypothesis of dark energy and this alternative. But that's another alternative, of course. Um, okay, guys, I'm just looking at the chat and see if you guys have any more questions. And but if not, well, I mean, you will be happy to know. I hope you will be happy to know that Dr. Pamela is coming back tomorrow, and I hope you had a little bit fun with me and that you can actually go and do a little bit more of research on the stories that we found out today. That which this is just a little teaser to get you guys doing your own research and yeah, asking more questions. But yes, what is my Twitch username? That's a good questions. I do have one. I don't have it right now here, so I'm gonna ask Pamela to maybe convey to you tomorrow. Thank you very much for asking. Um, but yeah, Okay, guys, thank you so much, and maybe I'll see you in another chance. Bye. Ciao.